So today we'll be talking about cell compartments. Okay, how can you model a cell that is more complex than what we've been doing before? So usually when you just start to use comp cell, or cell is just a blob, right? The blob can have many shapes, can do many things, can have those reaction kinetic networks inside them. And so the cells can do many things, but sometimes you want to make our cells be a little bit more different, have a structure inside them. And today we're going to tell you how to do that using the concept of cell compartments and clusters, and how you can make a model that looks like this. Okay, so remember that okay, this meeting is being recorded and live stream on YouTube, so you can actually go back and watch this module later. This, feel free to use all the buttons on Zoom. Yes, no, go slower, go faster, to communicate for us to adjust our pacing of the teaching. And please add your questions in the chat, right? If you have any problems, someone in the chat may be able to help you, okay? And the videos and all the exercises have been made available to you on the student materials folder, okay? So the topics for today's course will be, well, motivation. I'll talk about different ways that you can have implement cell compartments in comp cell. I'll talk about the difference between internal and external contact energies. Sorry for the typo here. And then we're going to create an epithelium comp cell 3D, okay? And we're going to also create crawling cells, okay? Actually, we'll be creating the crawling cells first and the epithelium later. Switch the order here. Okay, and I forgot to update. So, as you all know, or if you do not know, you'll be knowing now, is that cells are, they have, sometimes from the outside, the cell may look like it's isotropic, but definitely when you look inside the cell, it's not isotropic, it's not homogeneous, it's made of many different materials. You have the nucleus, you have the Golgi apparatus, you have centrioles and mitochondria, you have vacuoles, you have many of different structures and organelles inside the cell that make it to behave a little bit different from one side of the cell and the other side. So if you poke the cell from one side, you actually may feel a little bit different, okay? And those cells have those structures, right? And then they may be, and for some applications, some models, those internal structures might be very important if for your simulation. Maybe you want to model for example, the nucleus of the cell to be slightly stiffer than the cytoplasm of the cell, or sometimes in some simulation, you actually need explicit model of the membrane of the cell that's different from the cytosol or the cytoplasm of the cell. So sometimes that differentiation is very important for a model. And this is something that can be easily done using the cellular pulse GGH framework, okay? Sometimes your cell is actually strikingly different when you look from the outside. So if you look at a cell that's crawling on the surface, right, there is a clear front edge of the cell and a rear of the cell in the middle of the cell, okay? So here on the top left, you see a cell crawling, and then there's different, very different cells. You can use things like surface constraint and length constraint to make the cell look different from the outside, but sometimes you want to actually, so many times that's not enough to give the shape of your cell. Many times you have to actually make the front cell to look exactly and have very many different properties that are different from the rear of the cell or the center of the cell. And if you're doing a cell crawling model in 3D, you maybe want to make have the nucleus inside, because that the cell actually goes up around the nucleus as it moves, and the front of the cell is very flat and stays very close to the surface at which the cell is crawling onto. The other place where you see cells that have a highly structurized, have many different properties as you go along the cell axis, is when you talk about epithelial cells. So here in this picture on the bottom right, you see an epithelial cell, part of a tissue, right? And this cell has very different properties on its bottom against its top. So the top is the apical region of the cell, where the cell is usually facing the lumen or some kind of liquid. At the middle of the cell or the lateral sides of the cell or center of the cell, we have those adhesive belt, adhesion junctions, right? The cells are strongly connected to the neighboring cells to ensure that the epithelium is does not fall apart. And at the bottom side of the cell, again, it's physical, chemical, and signaling properties may be very different because that's the part of the cell that's actually attached to the extracellular matrix that sits beneath the epithelium, right? So all those different cell regions, so apical, central, and basal, they have different adhesion properties. They may have different different activities. Usually the apical side of cells may undergo constriction, right? Here on the more towards the basal side, you have the desmosomes, where it's kind of adhesion between those other cells that they do not undergo constriction, but they make very tight belts between one cell and the other, right? And that usually what gives the most of the structure of the cell and of the epithelium. And then the cells want to attach to the basal side, and the basal side of the cell actually may be moving. There are instances where the basal side of the cell actually have protrusions, and the cell actually move on the basal side, and the rest of the cell body just follow along. So the take-home message is that the cells are highly heterogeneous, especially inside the cell, okay? And many times you want to model this spatial heterogeneity within the cells. And you can do that using the concept of cell compartments in the cellular plots model, GGH models, okay? So when you talk about cellular compartments in Compartmental 3D, there are basically two ways in which you can actually subdivide the cell. So here you can see that, okay, you see a single cell on the top and a collection of multiple cells at the bottom, okay? So you can either subdivide your cell in terms of, in such a way that your compartments actually correspond to real structure of the cell. For example, here on the top, your cell is made of 3 compartments. One is the membrane in green, you have the nucleus in blue, and everything else you kind of put together as the cytoplasm of the cell, or the thing that's neither the membrane nor the nucleus. You just kind of homogenize together in your model of the cell to be the same thing. So this is a way that you can subdivide your cell, where you can, each one of the cell compartment actually corresponds to a very well-defined organelle or substructure that make part of the cell, okay? So this is the explicit compartmentalization of the cells that you can have in CompCell. Another way that you can do it is to compartmentalize the cells in a more abstract way, and that's usually what we do when you're made or an epithelial model of the cells. Okay, so if the cells are epithelium, right? Then you actually subdivide your cell into apical, lateral, or central, and a basal side of the cells, like you see in this picture. So here, you see many different cells. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9 cells, and each cell is divided in the apical part, which is the top part, core, lateral part in the center in red, and a basal part that's actually touching the extracellular matrix in the bottom, right, which is the basal part of the cell. So the cell in reality is not structured this way, okay? There's not a boundary between apical and lateral, and a boundary between lateral and basal, right? Everything is continuous, but this is just a way that you can model those different compartments of the cell and assign them different properties that reflect the abundance of structures, subcellular structures that are more present in the apical side and that are more present in the basal side, and so on, so on. Okay, so there are two ways that you can use compartments, either to actually correspond to specific structures as here, see here on the top, or to more functional parts of the cell that you just are abstractly dividing your cell into, like here in the epithelium, right? Okay, hope this makes sense. So the use of compartment cells, cell has something that people do use in their research. Okay, so the very first time that they actually use it, or that was published that they use it, is, for example, there is this paper by John Starros and Andreas Deutsch from 2007, where they model myxobacteria. So it's kind of a worm made of a very long worm, and they want to use composite model to model it. And the way they did, they each one of those myxobacteria is made of many little cells. Okay, they are connected along with, and then those cells are usually the same, okay, except for the front and the back of the cell of the bacteria, so that this one moves and then these other ones just follow along, okay? All right, so this is one way. Then the other thing that you can use your cells is actually to model epithelium, like you see here. And here you see an epithelium where the cells here at the bottom, they undergo apical constriction, and the cells here on the basal side, they actually inflate and change their volumes. So you can, when you use compartmental cells, you can actually assign different properties to each one of your subcompartments of your cell. And so here, if you make those cells kind of smaller and this one's bigger, and actually you add links, which we're going to be talking about later, to make the cells actually get close to one another, you can actually induce invagination process like this, and you actually butts out this structure and you form a new vesicle, another kind of, yeah, well, it's not a vesicle, it's an epithelium ball that detaches from the underlying epithelium from which it emerged from, okay? So, yes, I'll get there. The other way you can use compartment cells is actually to have cell compartments that are dynamic and they can change places within the cell. And that's a very powerful way to use compartmental cells when those structures are not, those subregions of the cell are not fixed on the cell, but actually can diffuse within the cell, and the cell just kind of sort out its compartments according to the external environment. So that was used in this paper from 2016, where those compartments, they are not fixed in space inside the cell, but they can move along, and that allows for your cell to be highly dynamic and adapt very quickly to its environment. And so in the case where you have epithelium that's just growing, you don't have to, every time that you make a new cell, you don't have to assign where the basal is, where the apical is, or where the core is. You can actually self-sort according to the environment. So that's something that you're going to be talking about tomorrow, okay, how to do these dynamic compartment cells. And with those dynamic compartments, you can model a very lively epithelium, like in this case of this nephron that you see here. And you can also model processes like PCP patterning, okay, which is an exercise that you're going to be doing on next tomorrow. So PCP, very quickly, there's going to be a proper introduction to it, but is when the cells are making epithelium, right? They have this other polarization that happens on the plane of the cell, usually on the apical side, where you have a sort of proteins that kind of sort out due to the contact interaction with the nearby cells. So that gives a polarity of the cells that be used to actually specify some tissue level properties. In the case of the Drosophila wing, would be direction of the hair cells on the wing of the Drosophila, or can be guide other events where the cells need to be polarized for your phenomena to actually happen in a coordinated way. So you'll be doing models like this where the compartments self-sort, okay? And that will be tomorrow, okay? So these slides are just kind of a way to tease you of all the things you'll be learning how to do when you use compartmental cells. And then a question that have been in the chat, right, is Why you're talking about this? Have you not done this before? I'm pretty sure that I saw Gilberto showing this simulation here. So yeah, it's true. When Gilberto gave this talk on 4.2.2, right, he did use compartmental cells, okay, but not very explicitly. Your cells did have three compartments: a front, nucleus, and a cytoplasm, right? That's true, okay. But when he did that, for simplicity, he did not use all the features that Compartmental has when dealing with compartments, okay? Because if you take his model, okay, and you add two cells or more to it, this is what will happen, okay? So here's a model with two cells, okay, and they're happy, right? But the problem here is that if you just wait a little bit, if the cells touch each other, they do not know which compartment belongs to each cell, and the cell usually fuses, okay? So if you do that with 4 cells, then this becomes more of a problem, because as soon as those cells see each other, they do not know what does this nucleus belong to me or to other cytoplasm, or where. So it becomes very confusing, right? Because the contact energies are the same between all the compartments or all the subcells, and if you have more than one cell, these kind of problems will start to happen, right? So the way that you avoid that is by telling cell that, okay, this nucleus belongs to this cell, this cytoplasm belongs to this cell, and this front, this umbilical belongs to this cell, and these 3 compartments belong to this cell, okay? So what you have to do is find a way to tell cell that this belongs to this one, and these compartments belong to that one, okay? And so when you do that by assigning the cells a second ID, okay, which will be the cluster ID of the cells. And when you not only have to do that, but you also have to say that those compartments here, between themselves, they should have a different contact energy between them than those compartments have when they found a cell that belongs to compartment belong to different cell. Okay, so that's how you differentiate. So let me walk you through again exactly how that's implemented in Compartmental 3D. Okay, so for this, we need to add a new concept for your contact energies, with the concept of internal versus external contact energies. So when you create your cell, your model of a crawling cell, okay, and you want to use compartments, you tell in the wizard, okay, I want to use cell compartments, right? Or I want to use contact energies and internal contact energies. So both of them are going to look like the same. It's basically a table of energies that the different cell types have one another, but there is one table for when the cells belong to different clusters, and another table when their cells types belong to the same cluster, okay? So the contact energy that you have as a default in our Compartmental 3D simulations, okay, is the one that says interaction between cells that belongs to different compartments, okay? And the new table that you get, which is the contact internal, okay, well, the name already says, sets what to be the contact energies, interaction energies between cells, cell types, when they belong to the same cluster of cells. Does it make sense? Okay, so this one here, that's the new one that you will be dealing with, sets the contact energy between internal compartments, okay? And if you want to create a crawling cell like the way we have when we did the exercise with Gilberto, right? You can basically use the same original values that you would have used on the exercise 4.2.2, okay? So for this one, you can actually for the exercise that we're doing later, we can actually use the base code that you had at the end of the module 4.2 with Gilberto, okay? So this here with the contact between lateral and cytoplasm, nucleus and cytoplasm, and nucleus and lateral, and we can use the same energies that you have used with Gilberto. And if I'm not mistaken, they should be 11, 10, and 40, okay? Now, these diagonal values here can be ignored because our compartments only, or clusters only have one cell type of each, one copy of each cell type. So they only have one nucleus, they only have one cytoplasm, they only have one lamellipodia. So these energies here are never used, okay? Because they only have one copy of each compartment type, okay? In some models, you may want to actually have multiple. Maybe you want to use a model service 2 nuclei, right? Then in this case, you have to set what's going to be the contact energy internal between 2 nuclei that belongs to the same cluster, okay? Or something, if you have kind of similar situations, then you have to set these contact energies. But in the case of a crawling cell, you're going to keep things simple, and you only have one copy of each cell type inside. Does that make sense? So this is how you use the internal contact energies. Then at the same time, we're going to have the external contact energies that sets the energy between compartments that belong to the different clusters, to different cells, okay? So here, this will set the contact energy between external compartments, okay? And again, because you're dealing with external compartment, and medium by itself is an external compartment to your cells, then in this case, you can still use the same old values that you have from Gilberto's simulation. So I believe, if I'm not mistaken, you use 22 for cytoplasm medium, 10 for lamellipodia medium, and 100 between nucleus and the medium. Why he used such a high energy here? Because he wants that to ensure that the nucleus stay inside the cell and never touch the medium, because the nucleus has to be inside. So that's why he uses very high energy here, and comparatively low contact energies for the other one, because those other two, they are supposed to be interacting with the external medium, okay? And now those other thing, other values here, okay? We have to reason out what those contact energies should be, okay? So we have to reason out those values, okay? So what do you think those values have to be? Do they have to be high, low, or they should have no effect? So I want now to think about, okay, if I want to make sure that my cells, when they come together, they do not mix like happened in the previous movie, which values of those energies should I use? Please tell me in the chat. The higher possible. Okay, the contents of the media have already been set here on the first row. High for all nucleus because it should not touch anything. Yes, very good. That's true. Yes, okay. So yeah, definitely you want to make it very high for the nucleus, right? So that's going to be the next slide, because you want to prevent it from touching the compartment of the other cells. You want to prevent it from touching the medium, and even more to actually touch the compartment of the other cells. So for the nucleus, you definitely want high. But what about the other three here? Do you want to be as high, or maybe can be a little bit lower? Okay, the internal ones are here. Yeah, the C wants to touch L, and wants to touch the nucleus for sure. So they are low here. So when you talk about the C cytoplasm with the other lamellipodia, the other cytoplasm, okay, should that be about the same? Should be higher or should be lower? Maybe just higher than 11. Yes. So that depends, okay, on your model. So do the cells like to get together and walk side by side, hands touching, or the cells kind of touch and kind of, they don't really like to be together with everyone. Okay, so that actually will depend on your model, but usually, as a rule of thumb, yes, you do want those ones to be slightly higher, maybe high, uh, if you want to make them to be like this. So here, those three energies are basically setting those three arrows here: cytoplasm, lamellipodia with lamellipodia, and the cross between different lamellipodias with different cytoplasm, right? So usually you want to have those highs. So in the exercise that follow, what you want to do is that first you will be dealing with two adhesion energies tables, right? And choosing the correct values, right? Values that work is a little bit of an art, and you need practice to do that, but it's something that you can reason out. Okay, so the best approach to this is not kind of random select numbers, but think about, okay, what should be high, what should be low, what should be in between, and between those in between, what should be the hierarchy of energies for my system to actually behave correctly. Okay, so that's now what you're going to do in the next set of exercise. Okay, so our first exercise of today will be, okay, let's create a simulation with many moving cells, use the cell compartment features in CC3D. So we must use the contact internal plugin, specify the initial compartments belong to the same cluster. You have to, if you want to have something that looks like this, you have to implement cluster division, and there's a special set of commands on the Python level that makes your cluster cells divide, okay? And we also have to use, once the cells start dividing, right, and then you have more than two cells crawling and interact with one another, you have to choose the appropriate set of contact and internal contact energy values, okay? So let's go to our first exercise, which is the use of the contact internal plugin. So is everybody ready? So you should all have, so let's do exercise 6.1.1a, create a multiple crawling cell model. And for this one, we're going to start from the exercise cell module, oh, sorry, not 2.4, should be 4.2, okay? And you can download a new version of it from the student materials, and should be under file 6.6.1a.zip. So I'm going to give a few seconds for all of you to find that model in the student materials folder and download it, unzip it, and open that in Tweedit, and you're going to start from there. Okay. Hayden already put a link to the chat. I'm going to give you guys 1 minute to download it and make sure you have open on Tweedit on your computer or on NanoHelp. Should be 6.6. Oh yeah, there's a typo here. Should be 6.1.1a. I should fix this here right now. Okay. This way. All right.
Julio, in the provided exercises, there's no 0.1a. There's just a 6.1.2, and then it goes straight to B. I think 6.1.2 is the one people need, right?
Okay, let me check here. Now 6.1.2 is tissue folding, is a different one. Okay, it seems that I have made a mistake. So let's do the following. I'll do a live coding now. Oh, maybe that will not be that bad. Let's just create that file. Okay, so you can still see my screen, right? So let's just create the cell crawling project. I'm going to create here. I'm going to call it module 6_1. Cell migration compartment, stuff like this. I will hit continue. Let's leave everything like that. Hit continue, and let's now add the types of cells that you should have. So you should have a now. Well, instead of doing that, let's just go to the student material folder and download the model that Gilberto has. Okay. So it should be E4222, I believe. Okay, I have this version E4222. Here, let me play in the player. And this is what I have when I run that simulation. Okay, a cell that's moving this way. This is let me do something. Okay, so let's use the file e4.222.cc3D. I'm very sorry about the confusion here. Okay. I must have accidentally deleted the base file, and of course, if I did that, I end up not sharing the file with you. Okay, so if you run the simulation, opening player, you should all get something that looks like this. You should see a single cell moving on the screen like that, and just adjust the colors, okay, to match what I have on my slides. So nucleus is white. So one thing that I want to do is I don't want to have, I want to set the cell cluster boundary to be white. In the color, I want black. Okay. Cluster boundary, I want to be white. Okay. And cell boundary color, I want to actually not visualize. Okay. So when I run simulation, this is what we see. We should all get a working simulation that has the cell crawling like this. So did everybody got this? I agree. It would be great if you can have that interface here. So this file everybody should have this file. Okay, so we're gonna use this base file as for our simulations, okay? And what I want to do next is to actually, let's open that in Tweedit and take a look at what is happening there, okay? So it runs as expected from Gilberto's course, okay? So it has the cell type section, let me make this a little bit bigger. Okay. It has the three cell types, cyto, lamel, and nucleus, okay? It has an external potential plugin that actually what makes the cell move in particular directions, okay? The cells have volume, center of mass, and here is a table of energies that the cell types have with one another, okay? And I believe these are the same values that we had before. So medium cycle is 22, 10, 100. I believe that's exactly the same, okay? Cycle is 15. Well, they don't have an effect right now because we only have one cell, okay? And then it's 10, 11, and lamellipodium with nucleus is 40, okay? Because actually we don't want those two to touch one another, so that all makes sense. And then in the uniform initializer, you're actually starting all the cells very close to one another, like this, okay? So if I just stop simulation and play again, stop, just hit the step, yes, okay. Oh, it crashed, then open again. Save. Open player, ignore. Stop, step. Okay, you are starting the three compartments right next to one another, okay? And because of that nucleus doesn't like the medium, right? You're gonna quickly go inside one of the other two cell types to hide from the nucleus. And the nucleus actually prefers to be surrounded by cytoplasm and surrounded by lamellipodium. So we're gonna run towards the purple one here to hide from the nucleus. So we're gonna just step here. They start interacting. We actually have changed the energies, so the volumes. And then here, you see that the nucleus go inside, okay? So that's the first thing that happens. You see the effect of the contact energies shaping the basic morphology of the cell, okay? Then what you have later is that the cell, if I just play simulation, will start to move in the direction of the lamellipodia, right? And then if you can look here, the steppables, okay? This is what happened here. So in the stepable files, you see on the start function, the first thing you do, you go over all the cells, okay? And assign the volumes, okay? So the cytoplasm will have a volume of 300 lattice sites. The lamellipodium will have a third of 300, so it will be 100 lattice sites. And the nucleus will have a fifth of that size, so it will be smaller, okay? And then you also assign the lambda volume, and then the cell themselves have no directionality, okay? So there is external protein that makes the cells move, okay? They are set to 0, but then as the cell time goes on, okay? So here in the step function, you define a variable called time interval to be 1,000. So every 1,000 Monte Carlo steps, you go over all of the cells, okay? And for the cell of cell type lamel, you assign a random direction, okay? So the cell will move towards this random direction, and then that's how the cell is changing its direction, as you see here, okay? So that's how the model works, okay? It's moving and change size with no proliferation. Okay, so does everybody has a working model that looks like this? And does this working model make sense to all of you? Yep, okay, great, thank you very much. Okay, so now let me continue my set of slides, okay? All right, so it's there, it's working, okay? So now what you want to do to the simulation, because you want to add more than one cell, okay? We have to add the contact internal plugin, okay? To do that, let's go to the XML file, okay? Let's go back to the XML, so making sure that you click here XML, all right? And then you can add plugins to your existing code without have to run through the wizard again. So the way you do that, you have to go back to XML, right? And when you are in XML, you can actually activate the CC3D ML option in the Compartmental menu. The only thing that you have to be careful is that you want to make sure that your cursor is at a place on XML where you can actually add a new line of code. And the best place to add this new plugin is going to be right after your table of additional energies. So here, make sure that your cursor is right below the contact plugin. Okay, so let me go back to my code here. I'm going to go to XML. Okay, here, double click, right? I find, okay, here's my contact energy. Let's make a new line below it. Okay, so my cursor should be between the contact and the uniform initializer. Okay, and once it's there, you can go here to Compartmental 3D ML. Click here. For some reason, this is not activated here on my edit. Okay, but it should be under plugins. You should be able to click plugins and select the contact internal. Okay, and once select contact internal, it's going to place the plugin contact internal right below the contact plugin of Compartmental. So when you go here, click here, you should paste this a new table of called contact internal. Did this work for everyone? Yes, yes, okay. So make sure that the contact internal is separated from the other one, okay? Make a copy of the cells initializer. You got more medium lines. Okay, if you got a medium line, you can delete them because medium is never part of the a cluster of cells. So if you got the medium lines, you can just delete them. Okay. Ideally, you should not get any medium option here. Okay. If you got, you can ignore them. But, or just delete them to make it simpler to you. So if you just add this here and hit save, okay, and if this plugin is an appropriate place inside your code, okay, and you run simulation, you should just see the same simulation exactly as you have right now, okay? So make sure that you add there. Don't worry about any of the values that you have there. If you have cell types medium there, you can just leave them there because they'll have no weight on it. If you want, you can delete the medium, the cell, the lines that have medium, but you don't really need to. Okay. So what you can do now, with this, we actually set up, or in our plan, we add the contact internal plugin to our worker simulation. And now you want to specify that the initial compartments that you just make the initial cell there actually belong to the same cluster of cells. You want to tell them that, okay, those three cell types that you put there right at the beginning, actually, those three ones there that you see here actually belong to the same cell. You have to tell Compartmental that they actually belong to the same cell. Otherwise, Compartmental will not know about that. Okay. So the way you do that, okay, I have to give a little bit explanation on how that really works on CompCell. So when you make a simulation CompCell, okay, all those different cells that you add on CompCell, they have a unique ID, which is called the cell ID of the ID of the cell. And you can access what this ID is by just typing the Python method cell.id. It's going to return the ID of the cell. So this ID is going to be the social security number of each one of your cell objects there. So each cell will have a unique ID, is a number that specifies, okay, so every lattice site will have this kind of this cell ID number, right? That specifies, okay, that this lattice site belongs to the cell, the red cell, which has ID 2. This green cell has ID 1. This other green cell here has ID 3, so it's not the same as 1. So that's how you know that those two cells are different, because all those lattice sites here has ID 3, and all those lattice sites here has ID 1. Okay. If you don't delete the median lines, the cell will still consider them as separate, because you have not actually the cell by default consider all the cells that you have simulation to be separate cells. Okay, you have to specifically tell CompCell that those two cells here belong to the same cluster. Okay. Okay. So far, if run simulation, it still works. It has a containers, but it's not being used because none of those 3 cell types that you add there at the beginning are you didn't tell CompCell that they belong to the same cluster. Okay. So going back here to my idea is that all those cells have the same has a unique ID. So when you look at those cells in our simulation, like the nuclei has ID, let's say 24, the cytoplasm has an ID 32, and the lamellipodia has ID 107. Okay, so these are not random; they usually are added in sequence. Okay, so you likely be 1, 2, and 3. Okay, depending on the order which operate the cells. But the point here is that this number can be anything, and they're always unique to that cell. Okay, and that cell ID cannot be changed. You have the ID number, that social security number, you cannot change it. Okay, it's always going to be the same. So how are you going to group those cells together? How are you going to tell them, okay, that those all 3 cells here belong to the same cluster? That's done by assigning the cells a second ID number, which would be some kind of, let's say, the family name of those cells, okay? So in addition to a cell ID that each cell has and is unique, you also have a cluster ID that's going to tell, okay, that all those cells belong to the same cluster. So when you use contact internal, you are actually use the cluster ID of the cells. Okay, so the cells will have its ID in black here, 24, 32, 43, 59, 88, 85. And on top of that, those cells also have a cluster ID, which can actually be the same between different cells. So here, this cell here will have a cluster ID of 2. So they have 2 numbers, 1, which is your own unique number, and another number, 2, 2, 2, that's going to tell that those 3 compartments belong to the same cluster. So is the cluster ID of the cell, that's how you access that information from the Python level. Okay, so here we have 2 nuclei, 2 cytoplasms, 2 lamellipodia. Okay, each one of them has a unique cluster cell ID, but they also have their own cluster ID. So all those these nuclei, these cytoplasms, and lamellipodia has a cluster ID of 10. So they make a single cluster, which is different from this one because this nuclei, this cytoplasm, and this lamellipodia here has a cluster ID of number 2, so that they belong to a separate cluster from this one. Okay. And the way that you have to do that, you have to go into your code and say, okay, you have to find this nuclei and say, okay, these will have a cluster ID of 2, this cytoplasm will have a cluster ID of 2, and this lamellipodia will have a cluster ID of 2. Therefore, they're going to use the same, they belong to the same cluster. And when they interact between themselves, they're going to be using not the contact energies, but they'll be used as internal contact energies. The same thing for this one, because you have assigned all of them the same cluster ID of value 10, when they interact between themselves, they'll be using internal contact energies, and when they interact with other objects that have a different cluster ID, then they'll be interacting using the external contact energies between themselves. Does it make sense? Okay, I hope it does. So let's continue. So now that specified that the niche compartment belongs in cluster, okay. Okay, so that's what you want to do. Okay, so now let's actually go and do the simulation, okay. Actually, Julio, it does not slow down simulation because you're still looking over table value. So the impact on the slowdown simulation is just the same. It's just you look at the two cells, we have different ideas, you just go to the table, grab the value and use that when you calculate contact energies. So it's just an if statement that you add on top of it. But that if statement was already there anyway. So it's actually the simulation does not slow down by it's very natural. Okay. Okay. So the way you specify those cells, you have to tell that at the Python level. So let's go there and do this. Okay. So what you have to do, you have to go now to the Python steppable file and find the place where you actually set the volume of all the cells. Okay. So let's all go to that place in the code, which should be around line 12. So let me see if the same place here. Steppables. Okay, mine it's line 16. Okay, but you see here the code is exactly the same. Okay, as we have here, right? And what you're gonna do is gonna make a new line. Okay, after we set the lambda volume. Okay, and on that new line, we're gonna retrieve what's the cluster ID of the cytoplasm on the cell. Okay, so you go to make a new line after this one here. So after you find the cytoplasm of the cell, make a new line there, and on that line, go to the menu, cell attributes, Compartmental 3D Python, cell attributes, and select cluster ID. Because when you do this, you're actually gonna read, you're gonna find out, okay, what's the cluster ID of the cytoplasm cell, okay? So you read it. So make sure that you all get here. So I'm gonna do here on my code. I'm gonna here, make a new line, go to Compartmental 3D Python. Again, it's, for some reason, it's not turned on my 3D. Okay. There's some kind of bug happening on my computer right now. Okay. But you should add this new line, so but it should be I can just type cluster new ego cell dot cluster ID, and it should work. It's plasma simulations running. You do inside the first if, okay? Because you find your first cell type, you want to grab the cluster ID of that cell type. So let me see if there's simulation. Maybe I can close the player. No, that didn't work. Okay. There's something wrong. So make sure that, so the idea is that, okay, when you look at this code, you're grabbing all the cytoplasm cells, then all the lamellipodia cells, and then all the nucleus cells. Okay, we only have one cell when we begin of each one type. So what I want to do is want to grab this cluster ID, and then when you go to the lamellipodia, you're going to make sure that this lamellipodia will have the same cluster ID as this one. Okay, so make sure that you all get here. Okay, so hopefully these options are working on your computer. Okay, so you should get this, and after you get this, okay, I want to reassign that value to the next cell. So I'm gonna go to here on the lamellipodia, make a new line there, and then I'm gonna reassign. I'm gonna tell that the cluster ID of the lamellipodia will be the same value as the cluster ID of the cytoplasm. And the way you do that, you go here, make a new line, okay, CC3D Python, cell attributes, and you select cluster ID reassignment, okay? And after you do the cluster ID reassignment, you have a code like reassign cluster ID of that cell, and that's going to be the new cluster ID of that cell. And what you put here is going to be the same value that you retrieve from the first one. And you do that for the lamellipodia and for the nucleus. Okay. And when you do that, you're explicitly telling CompCell that the lamellipodia will have the same cluster ID as cytoplasm, and that the nucleus will have the same cluster ID of the cytoplasm. So all those three cell types will have the same cluster ID. Okay. So I'll give you a few seconds for you guys to do it. So when you do, save simulation, play, and make sure it works. By default, the CompCell, when you get this code here, it assigns a random number. Remove that random number with the value that you retrieve from the first loop. Okay, so please implement that on your version of the code, and tell me what you get at the end. Yes, Shilai, it does assume that it's true for this simulation. So for this particular one, we are safe doing that, okay? Because we only have one cell of each type. If we start with many different cells, then you not really have to use a different strategy. And actually, that's something that's going to be doing the next exercise. Okay, so Sharon said that it works, but it looks funny, right? So let's look at that. Okay, so if you want simulation now, does simulation look right? You should get something that looks like this, which kind of, that's something wrong here. Okay, so did you get something that looks like that? Okay, so so the reason why that happens, or Sharon has already given the answer, is because we didn't fix the internal contact energies. Okay, so the reason here is that before simulation was looking fine, because we are using the external contact energies, but now that you make your cells to be the same cluster, is not look at this table anymore for the interaction energies, is actually looking at your new table of internal contact energies. And by default, okay, all those energies are set up to be 10 in the code. Okay, so what you want to do, if you want your cells to behave exactly as it was behaving before, you have to copy these values here to the internal contact energies. Okay, so what you have to do right now is go back to the XML code, okay, and make sure that you copy these energies here to be the same one as here, okay? And you also want to change the neighboring order all the internal contact energies to be exactly the same ones you had before. Because usually the neighborhood of the internal contact is set to default to be 1, okay? Maybe it has changed in the very new version of Compartmental, but make sure you have this before and those energies here to be exactly the same as you had on the external contact energies before, okay? Okay, so I'll give you 1 second for you guys to do this. So please do that on your end and tell me if now the cell looks nice, is well behaved. Okay, at 3 speed has that said that simulation is better, okay? So if you do this, make sure you save, right? You save both the steppable files and the XML file, okay? If it's red, it does not save. And then you run simulation and you should start at least at the beginning, something that looks like this, okay? So let me everyone know if you got up to here. Exactly, Shlai. The content internal plugin only checks energy between cells which have the same cluster ID. If they don't have the same cluster ID, then what the cells use is the original contact energy table.
Julio, there was a question in the chat.
No, they don't need to. Actually, they will have to be different. That is what you're gonna see as soon as you have 2 cells. You realize that you have to revisit the external contact energy. Okay, but for now, let's just copy what had on the contact energy before to the internal one to make sure that our cell that now belongs to the same cluster looks correct. Okay, and as soon then we're gonna make sure now our next exercise is gonna be add cell division using clusters. Okay, and then when you do that, you see that something's quite not right, and then you have to go back to the external contact energy. All right, so if everybody got here and got a cell that's now belongs to, which a cluster cell, which still behaves nice. Okay, I hope you do. So let's now look at their next to-do list, which now let's implement cluster division. Okay, so I want now your cells to divide, so you have lots of moving cells like you see here in this movie. Okay, so to add division, it's simple. Okay, you go back to the XML. Okay, and on this table that you have here, Compartment project. Okay, right click on the steppable files. Right click or double click if you have a Mac. Okay, and then you have the option add steppable. Okay. So go here, add steppable. You click there. Okay. And once you click that, you should get a wizard. Okay. That say, okay, you want to create a new steppable, a new class, a new function, new feature to your simulation. Okay. And he asks, okay, what should be the name of this new steppable and what you should supposed to do. Okay. I'm not sure you have done this before, but that's a way from the tweeted to add steppables. Okay. And then just like divide cluster cell, let's give this the name of our steppable. And here on the steppable type, let's choose cluster mitosis. Okay. So give a name to steppable. Again, no space in the name. Don't start for number. Don't use funny characters. Okay, let's just use divided cluster cell, everything in one line. Okay, you can have the call frequency to 1, and usually you have the generic type. Okay, but for this one, we want to use the cluster mitosis, which is the way to divide the cells when they are actually made up of when they are a cluster cell made of many compartments. So ComCell can handle that automatically for you. Okay. So is everyone here? If you need help, please send a message in the chat. Okay. So again, right click on the steppable files here, should be the last one on your tweeted. Click add steppable, give the name to steppable and select cluster mitosis. And what should happen is you should make alterations to your both Python files, okay? Then you should get a text that looks like this. Okay, so you already paste a lot of code for you automatically on your tweeted. Okay, so what you have to do now is you have to go and over it to make sure that you're gonna divide our cells in a appropriate way. Okay, so you can see here that it creates a new class, divide cluster cell, and then adds the name steppable on top of it. Okay, and then the first thing is go over all the cells, right? For each cell type, it gets the list of compartments inside your cell, okay, and make a printment of this cell with this ID belongs to is of this type, okay, and then it has this mitosis cluster ID list, okay, which go over all compartments of the cells, collect the volume of each cell that belongs to the same cluster, okay, and then it check if the volume of the cluster, which is the sum volume of all the three different compartment cells above a certain value. Then it divides the cell using mitosis cluster ID lists. Well, you append that cluster ID to a list of cells to divide, and then you go over the cluster ID of the cells that should divide, and we divide the cells. And here it divides against some random orientation. Okay, so that's the code that you get at the beginning. Okay, this is breakdown. Okay, this is by just to show how you can handle the cluster at the Python level. Here's the part where you decide which cells to divide, and this last one is where you actually implement the division. Okay, so if this makes sense, let's now go to the next slide. Okay, so here is just showing how you can handle the clusters of the cell. Okay, we don't gonna really need work on that. What's most important is that here in the next part, let's change the division condition, okay? Instead of having more cells divide if they're a certain size, okay? Let's make divisions a random event. So in our simulation, the cells are not growing, okay? So it does not make sense to have a division condition based on the volume of the cell, okay? You just want cells to move and then suddenly divide into another one. So instead of having check the cluster volume if it's bigger or lower than a certain value, let's just change that by making if it's as a random event. So instead of having cluster volume bigger than 250, let's change that line of the code to be random, open and close parentheses, lower than 0.001. So the cells, every Monte Carlo step, they have a 0.1 chance of dividing. Okay, and that should be enough for the cells to divide. Okay. So please do this. And after you do this, okay, you can look at that here, that this is going to be the condition of which cluster will be dividing in your code. And then CompCell goes over all the cells that should be dividing. And then you have self-divide cluster in a random orientation. And then you specify the cluster ID of which cluster of cells should divide. And the nice thing about CompCell is that CompCell automatically reproduce the pattern of the arrangement of those compartments into the two other cells. So here, if you have a cell that's moving this direction and you divide at this orientation, what you have a lamellipodium on the top, cytoplasm, and a nucleus on the bottom. When it makes those two cells, it tries to place the compartments more or less in the same positions that you had before, which would be lamellipodium on top, cytoplasm in the middle, nucleus on the back, and then for the cell that the new cell that's here is going to be lamellipodium on top, a cytoplasm in the center, and nucleus more towards the back. Okay. What happens to the cluster ID of the new cell clusters? They got assigned a new cluster ID. So if the cell had cluster ID of 3, after division, CompCell is going to grab the next non-used cluster ID value. So, for example, let's suppose this has a cell ID of 1, 2, 3, and because you assign all the cluster ID to be 2, 2, 2, after division, these are going to remain the same cluster ID of 2, and those next 3 cells here will get a cluster ID of 4. Okay, so you not only divide and reproduce whatever arrangement of compartments you had before, you also make sure that the 2 other cells will have different cluster IDs. So CompCell 3D already takes care of all of that for you. You don't have to worry. Is the division along a random direction? Yes, in this code it is. But if you don't like this, you can change to these other options. You can divide the cluster along the major axis. You can divide the cluster along the minor axis, or you can divide the cluster along some user-specified direction that you set here, X, Y, and Z, and then you're going to always divide the cell in that specifically cut orientation that you have here, But for this exercise, you can just leave it as a random orientation. But if you want to change it, you can also do it here. So it's your choice. Okay. And the other thing that this code does, so you see that it's very, very similar to what you had on the mitosis plugin that you have used on the last week. It's just that everything now is done on the cluster level instead of the cell ID level. Okay, is that you also have an update attributes that you had before. By default, COMP assumes that you're dividing your cluster by growing the cell. So you always have this kind of, it automatically, it has a code to actually divide the target ID of all the subcompartments to have after that. But you're not really doing here. You're just divide the cells randomly, okay, as a random event. So you want to get rid of those two lines of codes. Right? So you just have, just get rid of them and just leave those two, okay? So your cells, after divide, they do not shrink. They actually grow back to their original target volumes. Okay, so make sure that on the depth update attributes function that you have inside your cluster mitosis class, you delete those two lines here or comment them. So both the parent and the child cell, the parent cluster and the child cluster, you have keep their target volumes as they had before. Okay, does it make sense? Is everybody following? Yes. So now you play simulation, you should see a cell crawling, and after a while, the cell should divide. Okay. And after it divides, tell me if everything looks okay or if it looks funny. So, do you guys got subdivision to work? If your cells are take too long to divide, you can go back and change that to a higher value so they divide. It stops immediately. Uh-oh. Check, Sharon, if you have some kind of random is not defined. Okay. So if random is not defined, add a new line below before that called import random. So you import the random library to your simulation. Or, okay. Add the line from random, import everything. So okay, yes. So if you add this line here in the code right before that, it should work. From random import everything, then the random function should be there for you. You can also, instead of using random less than this, you can use np.random again. Okay, after 4,000 steps, the lamellae separate, but the two nuclei are stuck together. Okay, so did anyone got something like that? So if we just run this simulation like this, what you have, you should get something that looks like that. Okay, the cell is there, crawling. Then the cell divide, but after the cell divides, everything gets stuck together, okay? And you do not have two separate cells that you had before, as you had before. Yes, cells fuse together. And lamellas are flying everywhere. Yeah, this eventually escape from one another. Yes. So what's wrong here? So what are we missing from the simulation? I think someone already had a question about that before. What about such and such? And that's exactly what is missing. You have to go back and now adjust the external energies. Okay, those cells, when after the cell divides, those new compartments do belong to different cells. Okay, that is working. The problem is that we are still using the same contact energy that you had before. Okay, you have to go back and choose appropriate contact energies to make sure that when the cell divide, they do not use, if you keep the internal contact energies, the same as external contact energies, okay, after the cell divide, the compartments are gonna still treat each other as if they belong to the same cell, because the energies are the same. So what you have to go now, do that, is go back to your code and make a good choice for the external contact energies, okay? So, so you have to, you want to make sure the cells are separated, not fused together, what you had before. So let's go back here to this table. And remember that we talked about this at the very beginning, right? We reason now that the contact energy of the nucleus with everything else that's external to that does not belong to the same energy should be high, very high. And that the other external contact energies between the cells and everything else should also be high, but maybe not as high as the nucleus, okay? So now I'm gonna leave this part up to you, okay? We had that this should be very high, this should be some kind of high, maybe not as high before, but I didn't specify how much they should compare to these ones. So go to your code now, go to the XML and change those values to make sure that the cells behave more like this instead of being fused together. So that's your exercise for the next 2 minutes. Go back to the code on XML and make sure that you change those values and then do that until your cells look satisfactory to you, okay? If you want the cells to completely separate apart, you have a choice of energies. If you want to actually not mind being stuck together, as long as they don't mix, you may choose a different set of energies. If you want your cells to actually be kind of following each other, you may have to use a different set of energies, right? So now it's up to you to try your own values and see if it works or not. I had trouble getting cells not to merge. Then I made much higher energies and crashed. Well, open again and try, okay? So I'm gonna share here. This is what happens if I choose 100, 100, 100, and 50, 50, 50. When I use those set of energies, I get my cells to look like that, okay? And this is just one possible solution for it. So because 50, 50 is still very high, so that ensures that the cells actually never touch each other, they immediately separate. So there is always medium between them. But if you do not mind the cells actually touch each other, or maybe you do not mind the cytoplasm to touch other cells, you can make the maybe this to be to let's say 22, right? Then the cells will actually touch the cytoplasm with one another. Okay. If you want to make other choice of energies, will give rise to different cell behavior, cell patterns as they move along. Okay. Then it's up to you. Okay, what you should use to you first decide what you want to see in your cells, and then we choose the energies until you get that appropriate behavior. Okay. Hopefully someone can help Sharon in the chat, okay, to see why her simulation is crashing. They're still stuck together. Did you use that on the contact plugin or the contact internal? Make sure that you made those changes in the correct place, contact, okay? Make sure you save simulation before you play it. Your cell split and have the nucleus behind. Oh, revisit your contact, your energies to make sure that everything is in place. Oh, okay. Yeah, then they really like each other, right? Because it's the lowest contact energy that you had in the simulation. Okay. If you got a cell that lost in lamellipodium after you do the division, right? The new cell will not have lamellipodium because it didn't have at the beginning, right? So if your very first cell for some reason lost lamellipodium, lost the nucleus, when you implement the cell division, CompCell does not know that it's supposed to have a lamellipodium there. So it just copies cytoplasm nucleus. And then, then you get all, well, headless cells without lamellipodium for the rest of your generation. Okay, maybe what might be happening is maybe the drive to make the cells move is too strong. Okay, so you may want to on the steppables, you may want to change this value here to be a little bit lower instead of 120 to be 100. Okay, this way the drive to put the cells is a little bit that cell should move a little bit slower. Okay, and then you are less likely to leave the nucleus behind. And also make sure that you have the contact energies as in here. Okay, if you make sure that the nucleus have very high contact energy, everything else, so it wants to stay inside the cell, and low contact energy with the cytoplasm when the cells belong to the same cluster. So they really like to be inside the cytoplasm with the same cell.
This issue with compartments lost during compartmental division is something very hard to deal with. At least from my part, I tried many solutions, nothing worked. In other simulations, I mean. So it's not a problem in the code, okay? It's really a problem with compartmental subdivision. It doesn't guarantee that the child cells will have all compartments. There's no guarantee.
Yeah, and the fact that we're not really growing our cells for make a division, right? Some of those compartments may be too small and are quickly lost after you divided them.
Yes.
So when you use compartment cells, your cells in general have to be a little bit bigger than before. So you make sure that they all have enough volume, right? So they will not get lost upon division.
Yeah, so for example, Julio, in your external contact matrix, you have nucleus set to 100, right?
Yes.
Once the cell divide, there will be two nucleuses of different cells in direct contact.
Yes.
So the best solution is to delete one of the nucleuses.
Mm-hmm.
So this is a source of this problem, losing compartments. And I tested solutions, for example. I didn't test the one possible solution, which would be to change the contact energy when you divide, and for example, wait a few Monte Carlo steps and then reset the energies. I didn't test that, but I tested, for example, setting the lambda volume very high, didn't work. I tried other stuff as well. But yeah, this is not a simple problem.
Well, one thing that maybe may help is right here, instead of having cycle volume 300, make it 500. So all the compartments will be bigger. And that would, you should not, maybe you'll solve the problem. It will be less likely for the compartments to disappear after subdivision.
Yes, yes.
Okay, Lampros found a different solution for his code, and I'm glad it worked great. Not sure that I completely understand what I just did, but if it's working, then that's great. Okay. So for those people that have the cells not disappearing, try to change this volume here at the step of from 300 to 500. Your cells are going to be bigger, but it should be more stable. Okay. So it's already 12:05. I'm behind. So we're gonna I'll stop here. This was a simulation where we actually use compartments to model the cells which actually have to represent a place of the cell that actually have a physical correspondence to what is in the cell. So we are basically exploring this case here. I have also a set of exercise that we use later on the final module today, where you actually model epithelium. Okay, I'm gonna leave that to after the break, or maybe I'm gonna just leave that to the next or to the final module. I have to decide that, but we're gonna stop here a little bit, and then when you go back, we're gonna resume from where it stopped, or just go directly to the use of links between cell compartments. Okay, so stop here, please. Finish the module questionnaire. Okay, and sorry about the for not have the correct code ready for you, so you spend a little waste 10 minutes on that confusion. I'm very sorry about that. But still, I thank you for your patience and understanding.